So my name is Cole Gibson, and I'm going to be opening my group's presentation on basic graph operations in Sage Math. So to begin, I just wanted to give an introduction of how graph theory can be used in real life, such as in topics like computer science. So graphs will model connections and networks, such as social networks, the internet, and transportation systems, with their algorithms essential for tasks like routing, searching, network analysis. These are all very complex topics that can be broken down into components such as basic graphs uh, for better understanding. So to begin, I'm going to explain how to make a graph from an edge list. So as you can see in SageMath, I declared an edgeless variable, and then the syntax for this variable is going to be a set of pair of vertices, such as vertex 0, 1, 1, 2, 2, 3. So edges are going to be created between each pair of these vertices. And to create the graph from this edge list, I'm just going to declare a variable and then create the graph from the edge list just like this. So once this line is run, I can show the graph like this, and it will create this shape here, where as you can see, each vertex that was in each pair is connected to an edge. So we have 0, 1, 1, 2, 2, 3, just as expected. So in addition to edgeless, we have adjacency matrices that we can make graphs from. So this adjacency matrix that I'm using here is going to have 3 vertices because there is 3 sets of brackets here. The syntax here, these x's are going to denote either a 0 or 1, where a 0 denotes that the current bracketed vertex is not connected to the index vertex. So that's kind of confusing, but what that means here is given that this bracket is vertex 0 is not going to be connected to 0, evidently, but will be connected to 1 and 2. Vertex 1 is not going to be connected to vertex 1, but is to 0 and 2, and so on. So if we run this line with the graph created from an adjacency matrix, we are going to get a graph that looks like this, which, as we expected, 0 is connected to 2 and 1, and then 2 is connected to 0 and 1, and so on. So SageMath also has a graphs class, which can make a lot of different types of graphs, but I just wanted to cover some of the more common and basic ones that we'll see here. So one of the important functions in this graph class is to create a complete graph, which will take a parameter as a number of vertices. So here running this line, we should get a complete graph with 8 vertices, which as expected does that. As you can see, each vertex is connected to every other vertex in the graph. Some other important functions that we have in this graph class is a path graph, which as expected is going to start from vertex 0, and it's simply going to connect an edge in sequential order to any of these. And then it's going to stop at the parameter -1, obviously because it starts at 0. In addition to this path graph, we have a wheel graph, which you can denote as the number of vertices as a parameter again. And it will start with 0 in the center, and then it will connect the rest of the vertices in a wheel just as we expected it to. And then finally, I wanted to cover some slightly more complicated graphs that can have different parameters to further manipulate them how the user would want. So for example, if we were going to create a complete bar type graph, in addition to the number of vertices, this function also takes a Boolean parameter. So if this Boolean parameter is true, the function will assign positions to the vertices so that the set of cardinality P is on line y equals 1, and the set of cardinality Q is on line y equals 0, which makes sense from the graph drawn here. And then in addition, another function to use as an example will be the complete multi-partite graph, which this one is pretty interesting. So it's going to take a vertex set that can be partitioned in a multiple disjoint set where edges only exist between vertices in different sets. So as you can see here, it's going to take this set here, and then it's going to only create edges between vertices in different sets. So for example, vertex 1 here is going to be connected to vertex 3, 4, 5, and 0, but not connected to 2. So that's just an example of how the edge creation works with this multi-partite graph. So yeah, the graph class has a lot of really unique types of graphs that it can make, and it's really powerful. These are just a few examples, but the possibilities are really endless with this graph creation. And that concludes this part of the presentation.
So I'm going to be going over some advanced graph functions in SageMath, and some of these are the cycle graph, the star graph, and the wheel graph. In graph theory, a cycle graph or circular graph is a graph that consists of a single cycle, or in other words, some number of vertices connected in a closed chain. A star graph is a special type of graph in which n-1 vertices have degree 1 and a single vertex has degree n-1. A wheel graph is a graph formed by connecting a single universal vertex to all vertices of a cycle. Now we're going to see how to create a cycle graph in SageMath. The code that I wrote is shown on the left side, and in this, the first line is using the cycle graph function, in which it sets the number of vertices to 5. And the second line displays the output, which is shown on the right side. And as you can see, it looks like a cycle graph. So this is how to create a star graph in SageMath. And as you can see, the code is shown on the left side, and it uses the star graph function in the first line, and it sets the number of vertices to 5. And the second line again displays the output shown on the right side. And this is how to create a wheel graph in SageMath. And again, on the left side, it shows the code that was written. It uses the wheel graph function, and it sets the number of vertices to 10. And in the second line, it displays the output shown on the right side. And as you can see, it looks like a wheel graph. Now we're going to see how to connect a disconnected graph. On the image on the right side, as you can see, this is a disconnected graph. This is because the vertex number 4 is not connected to anything. This graph is created in SageMath using the code that is shown on the left. It uses the graph function, and I have also shown how to check if this graph is connected in SageMath using the isConnected function. And as you can see, the result for that is false. Now we're going to see how to connect that graph. This is done using the add edge function shown on the left side. And this basically connects vertex number 1 and vertex number 4. And then we check if this graph is now connected. And as you can see, it is connected, as it shows true for the output on the right side.
I will be discussing the functions used to manipulate graph structures, such as adding and removing vertices and edges. Starting off with add vertex. Add vertex is a function which takes in one argument, v, which will be the name of the vertex that you want added to the graph, and it will add that vertex. It will create the vertex v in the graph if it doesn't already exist. Now, if the vertex already exists, then it will essentially not add anything to the graph in order to ensure there are no duplicates. Now, if v is not provided, meaning the vertex you want to add has not been provided, then the function will automatically use the least integer that's not already representing a vertex in the graph as the vertex that should be added. And you see an example of this below. As you can see in my before example, we have the vertices 0 through 9, a simple graph with the vertices 0 through 9. And in my example, I'm going to be adding the vertex 10 to the graph using two methods, one explicitly passing in 10, and the other not passing in any argument at all. As you can see in the after output, we're going to get 10 is going to be added to the graph as an isolated vertex. And this works when I don't pass in any arguments, since as you can see, my vertices are labeled from 0 through 9. The next smallest integer after 9 would be 10, and that will get added to the graph. So in this special case, either of these function calls can be made, and we will still have the same resulting output. The next function we'll be talking is add vertices, which is basically which has the same behavior as add vertex, except for the fact add vertices takes in an array of vertex or an array of vertex that should be added to the graph, and it will essentially add all these vertices to the graph if they don't already exist. Now, if an array is not provided, then no vertices are added. In my example, I'm going to be adding the vertices 0 through 9 to an empty graph, and as you can see on the right, this will be the result of will be the result of calling the function with these arguments on an empty graph. Next, we'll be talking about how to delete a vertex. The delete vertex function takes in one argument, v, which will be the vertex you want deleted from the graph, and it will delete the vertex from the graph if it exists. Additionally, it will also remove all edges that are incident to the vertex as well from the graph. As you can see in my before picture, I have a graph, a simple graph with the vertices 0 through 10. Now, I'm going to be calling delete vertex and passing in 10 as the vertex I want deleted. And as you can see in the after picture, 10 has been deleted, and the edge that was incident on both 9 and 10 has also been deleted. Delete vertices again has the same behavior as delete vertex, but it takes in an array of vertices as an input, and it will delete each one the vertices if they exist in the graph. Now in my before picture, again, I have a simple graph with the vertices 0 to 10, and I will call delete vertices on this graph, passing in 3, 4, 5, 6, and as you can see, the vertices from 3 to 6 have been removed, and so have all the edges that are incident on those vertices. Now we'll be discussing how to add an edge. Adding an edge, to add an edge, you'll need two vertices. You need two arguments passed in for it to behave how we expect it to behave, which is the first vertex and second vertex on which you want to add the edge. There's also an optional argument called label, which allows you to specify a label for the edge, which is useful if you want to, for example, assign a weight to an edge or assign a cost for an edge. Now, in my before picture, you can see that I have a graph within which we have a subgraph, which is a simple graph with vertices 0 through 9, and I have a vertex 10, which is isolated. Now, in my example, I'm going to be adding an edge from vertex 9 to vertex 10, and as you can see in the after picture, an edge has been added from 9 and 10, between 9 and 10, so it's incident on 9 and 10. Add edges, again, has the same behavior as add edge, except for the fact it takes in an array of edges that should be added to the given graph. Now, in my example, as you can see in the before picture, I have a graph with isolated vertices from 0 to 4. In my example, I'm going to be adding an edge between 0 to 1, 1 and 2, 2 to 2 and 3, and 3 and 4. And as you can see in the after result, after calling that function with those arguments, we do in fact have the edges between the given pair of vertices. Now I'll be discussing how we can add a vertex and an edge simultaneously. This can be done by using the method we discussed before, add edge and add edges. Now either function can be used to add both vertices, just depending on your preference and whether you want to add multiple pairs of edges, multiple edges, or just one edge. Now, how this works is if a vertex does not exist to which you're attempting to add an edge, then the function will automatically create the vertex or vertices for you and create an edge between them. In my example, you can see that I have an empty graph, which is my before. I'm going to be adding in edges between the vertices from 0 through 6, like 0 to 1, 1 to 2, etc. And what it will do is it will create the vertices for us, all the vertices from 0 to 6, and add the edge and add all the edges that we want added. As you can see in the after result, that is exactly what we get. All the vertices are added, and the edges have also been added. That concludes my section.
Hello everyone. I am Raneem Zamzami, part of the team for graph operations for this project, and I will be specifically talking about unions and disjoint unions of graphs. So to get started, we use Sage Math for this project. And before we get started, also I want to go over the definition of union. So a union of any set is a collection of what's in each of those sets together. So for example, if we have a set of 1, 2, and then another set of 2 and 3, the union of those set is 1, 2, and 3. So there's no duplicates. It's just if it's in both, it'll be you'll only have one copy of it in the union. So for this example, I created 3 graphs using Sage Math. So we have graph G, graph S, and graph J. So graph G is just consists of 4 vertices with 3 edges. And then S consists of 1 edge and 2 vertices. So as you can see here, for graph S, it's an edge between 1 and 0, which is also here in graph G, so 0 and 1. So it's the same edge. So when we call on the function, so G dot union S, we will get this function. So the reason that function looks exactly like function G is because these two are shared edges. So if you have shared edges, you will only have one copy of it in the union graph. So that's basically why we have like J exactly looks like G. So for our second example, we have another union of graphs, but this time graph S has only duplicate one duplicate vertices and no common edges. So as you can see here, this edge is connected to 1 and 5, and then here 1 is only connected to 0, and there's no vertices 5. So as you can see, when we call on to the function D dot union S, we get this function. So if we look at this part only, this looks exactly like graph G, but since it's the union, we will have both like G and S combined. So for example, here, they have the same vertices 1. So 1 is only appearing once, and that 1 is connected to 0 and 5. As you can see here, 1 is connected to 0, and then here 1 is connected to 5. And then for our next example, G looks like this. So it's only one edge of 0 between 0 and 1. And then S is also one edge between vertices 3 and 2. So when we call on to the union function, this is what we get. And then if you look closely, we have no common edges or no common vertices. So when we call on to the function, this is what we get. And they're not connected because they don't have anything connected or anything in common. So basically it's the union. So it's both of those graphs together, and that would be the union. For our last example, for the disjoint union, we'll be talking about disjoint union. So disjoint union is basically the union of all of the graphs, but they're not connected even if they share any common vertices or edges. So for example here, we have graph G and graph S, and they have the same edges, like one same edge and 2 same vertices, which are 0 and 1, and that edge in between. So when we call onto the function disjoint underscore union, this is what we get. So it's basically each of those graphs separated, but they're together. Like that's what J is, and that's what J is saved as. So when you call on to J, or if you want to show J here, as I did, it'll show both of the graphs, but separate. And yeah, thank you guys for listening. I apologize. I'm very sick, so my voice is kind of it's kind of very bad, but yeah. Thank you.
Hi, my name is Ayush, and I research basic graph operations regarding the loops on graphs in SageMath. The 4 functions that I decided to research thoroughly were number of loops, has loops, allow loops, and remove loops. So the first function here is number of loops, which returns the number of edges that are loops. Basically, this just returns the number of loops in one graph. Here, as you can see in the example, the code comes after Sage, and the output is a light blue font underneath it. So basically, in this is saying in this code, the graph of G has 4 loops. And as you can see, when the number of loops function is called for G, it returns 4, which is the number of edges that are loops in G. The next function is halves loops, which returns whether there are loops in the graph. This function is a Boolean, so the two outputs that can only come from this are true or false. As shown in this example, the graph of G has no loops, as there are 0 vertices, so when the has loops function has been called, it returns false. The next function is called allows loops, which returns whether loops are permitted in the graph. This function is a Boolean as well, so it can only return true or false. In this example, loops are set equal to true, so when allows loops is called for G, it returns true. The final function I researched was remove loops, which removes loops on vertices in a graph. As you can see in this example, when the edges function is called for G for the first time, all of the loops on the vertices are there. But after remove loops is called for G, the edges function is called again, and all the vertices that had loops were removed. As you can see, 0, 0, 1, 1, 2, 2, and 3, 3 are not there. So these were all the main basic graph operations that involve loops that I researched.
All right, so I'm going to talk a little bit about connectivity and the operations that check for connectivity and the connectivity of components, and then other connectivity-based features. All right, so the first two operations I have are is connected and is strongly connected, and what these do is check for connectivity of graphs in SageMath. So the first one I have here is connected, and it can be used on directed and undirected graphs. It returns true if the graph is connected and false otherwise. So the example I have here, I have a graph that is not connected. You can see that there's not a path going between each distinct pair of vertices. So when I ask SageMath if G, this graph is connected, it returns false. On the right here, I have it as strongly connected. And this returns true if the directed graph is strongly connected and false otherwise. So this can only be used on directed graphs. And in my example here, I have a circuit that is strongly connected. You can see that there's a path going from vertex A to vertex B, and then back from B to A. So when I ask SageMath using is strongly connected, if this graph is strongly connected, it returns true. All right, and then I have a couple operations that deal with connected components. So the first one I have is the operation connected components. And what this does is it returns a list of the list of vertices representing connected components. So these are ordered from smallest to largest. You can see using this sort equals true argument in my example. So I have 2 connected components in my example. And this, when using connected components, will return a list with 2 lists, one being 3, 4, 5, 6, the other being 0, 1, 2. So these are the vertices of the respective connected components in this graph. The next operation I have is connected components number. And what this says is it returns the number of connected components in this graph. So in my example here, there are 2 components. So when I call connected components number on G, it returns 2. And then finally, I have connected component sizes. What this does is it returns a list of the sizes of the components in the connected components in the graph. So I have 2 connected components here again. One is size 4, there are 4 vertices, and the one on the right is size 3, there are 3 vertices. So connected components sizes returns the list for 3. All right, I have 2 more operations dealing with connected components. The first one is connected components containing vertex. So this returns the list of vertices of the graph containing the given vertex. So in my example here, I have 2 connected components, and I call connected component containing vertex 4. So when I call this on my graph D, it returns the list 0, 1, 2, 3, 4, because that's a component that contains vertex 4. If I instead had asked for the connected component containing a vertex 7, SageMath would return 5, 6, 7 because the vertex 7 is found in that connected component 5, 6, 7. On the other hand, over here I have connected component subgraphs, and what this does is return a list of the subgraphs of the connected components as graph objects. So you can see below I have 2 graph objects outlined in blue, and these are the same 2 components that are on the left example for connected components containing vertex, but you can see it returns the list of subgraphs, the list of the 2 connected components as graph objects. So you can see that below on this example here. And then I have edge and vertex connectivity operations. So the first one I want to talk about is edge connectivity, and intuitively this returns the edge connectivity of the graph. So that's the minimum number of edges needed to be removed to disconnect the graph. So in a complete graph, this is also the minimum degree. So in my graph over here, it's graph G, I call edge connectivity on G, and SageMath will return 2 because 2 edges needed to be removed minimum to disconnect the graph. So for example, I could remove the edge from vertex 0 to 3 and then from 1 to 3, and that would disconnect the graph because you would have a isolated vertex 3 and then the rest of the graph. So the graph would no longer be connected, there would no longer be a path to 3. And then similarly, I have vertex connectivity, which is it returns the vertex connectivity. It's the minimum number of vertices needed to be removed to disconnect the graph. And this is always going to be less than or equal to the edge connectivity. So on my example here, again, using the vertex connectivity operation on G, you can see that the vertex connectivity is also 2. All right, and then finally, I wanted to talk about cut edges and cut vertices. So I have my first operation is cut edge. What this does is it returns true if the edge is a cut edge and false otherwise. So what a cut edge is if the edge is removed, does the graph become disconnected? If the answer is yes, then the edge is a cut edge. If the answer is no, then the edge is not a cut edge. So in my example on the right here, I have this graph G, and I call is cut edge on the edge from vertex 2 to vertex 3. And SageMath will return true because that edge right there is a cut edge. If you were to remove the edge from 2 to 3, the graph would no longer be connected because you'd have your isolated vertex 3 and then 0, 1, 2. So there would not be a distinct path between each pair of vertices. Similarly, is cut vertex returns true if the vertex is a cut vertex and false otherwise. And what a cut vertex is if it were to be removed, the graph becomes disconnected. So I ask here, I say, I call on G is cut vertex for vertex 1, and it returns false because 1 is not a cut vertex. If 1 were to be removed, the graph 0 to 3 would still be connected. There'd still be a path connecting each pair of vertices. But for example, if I had called is cut vertex on the vertex 2, it will return true because 2 is a cut vertex. If 2 were to be removed, again, you'd have that isolated vertex 3 and then 0, 1 would be connected. So you would have 2 connected components there. So that's what I have to say about connectivity and connectivity operations and connectivity functions on connected components.
All right, so I'm Caroline, and my topic was just some basic graph algorithms that you might want to use on pretty much a wide variety of graphs, really. Actually, most, if not all of these came from the generic graphs page of the Sage Math docs, and I figured, well, if you're looking for something that's widely applicable, that's where you'll probably find them. And so first I have Eulerian methods, one to find an Eulerian circuit and optionally a path instead, and one to create an Eulerian orientation, which is essentially kind of a new graph in this form in which each vertex is in degree is the same as its out degree. Otherwise, the orientation will be so that the difference between each vertex's in and out degrees is at most 1. And this one has no parameters. This one has a few. For the sake of time, while I have listed parameters, I'll only be going over the ones that are really applicable and important. All right, so this is the Eulerian circuit. ran it on a diamond graph, and as you see, we get false. And over here on the butterfly graph, we run it, and let's go back here. You can see I set return vertices to true, which prints a list version of the found path. And that's actually right here. And of course, it did find a circuit. So the first part of the input is this. It's a list of tuples that represent edges. And this here is a list that represents the vertices you travel to. So whereas this says 0, 4, 4, 2, this kind of trims out that it says you start at 0, then go to 4, 2, 1, etc. And then the Euler orientation, you can see demonstrated here. I started with a friendship graph, and just description here, digraph on 7 vertices. And I created a new variable to store the results of the orientation method. And when I showed that, ran the show method on that, this is what was output. As you can see, every vertex has an in and out degree of 1. So these are search and traversal methods. We have depth first search and breadth first search, which we talked about in class. It pretty much runs like you'd expect. The only required parameter here is start. You have to give it a vertex to start the search with. And so here we have the searches in action. And actually this graph is similar to the one I set to my background. It's a balanced tree. This is a different balanced tree though. Has the degree of 3 and 2 levels after that. So I ran both searches on this graph. And here we have the results of depth first. So it starts at 6 and it goes to 1, and then 5, and then 4, and then 0, and then 3. And as you can see, it approaches all the ends of the graph first, which is how we would expect it to behave. And breadth first, we also have that method, and I started it at 6 as well, just to get a better comparison. So here we have 6 goes to 1, because 1 is 6's only neighbor. And then we have all the neighbors of 1, 0, 4, 5, etc., how you would expect the algorithm to work. Here we have some methods to check if a graph is bipartite. We have literally is bipartite, which returns true or false depending on whether the graph is bipartite. And odd girth, this was a little bit interesting to me. I didn't know what girth was. I didn't know girth was a thing, but apparently it is the odd girth is the length of the smallest odd cycle of the graph. And as we mentioned in class, a bipartite graph does not have an odd cycle. So we'll see an example of that in action in a little bit. Here we have run the method on a circuit and a barbell graph. Here we have true, it is bipartite, and here we have the method returned false. And this true is just returning the cycle it found to disprove the bipartite status essentially. And here we have 1, 0, 2 for a cycle, and that is an odd cycle. And here we have the odd girth method, and we see that it returns infinity when the graph is bipartite. So that's another way to tell. And here it prints the length of the cycle we saw in the previous slide in the vertices. Then we have some isomorphism methods. Is isomorphic and is self-complementary. I included self-complementary here because it relates to isomorphism with the graph's complement. Here we have a cycle graph and a complete graph. And I ran is self-complementary on both of these. For the cycle, it was true, and for the complete graph, it was false. Obviously, as we talked about in class, the complete graph would be a 0 graph. It wouldn't have any edges. And then I compared them to each other. Are they isomorphic to each other? And no, they are not, which is as we would expect.